Hello everyone, my name is Shubhankar Pal and I'm a final year PhD student at the University of Michigan. I welcome you to my talk titled HetSim, Simulating Large-Scale Heterogeneous Systems Using a Trace-Driven Synchronization and Dependency-Aware Framework. I begin by thanking my colleagues from the Universities of Michigan and Edinburgh for their effort. As we all are quite familiar with, the end of Dennard scaling and slowdown of Moore's law has spurred the growth of heterogeneous architectures that are composed of different kinds of computing units. Further, the computer architecture community has seen a shift in focus from accelerating compute-bound workloads to memory-bound ones as a consequence of the rise in heterogeneity. Trace-driven simulation techniques that generate memory and compute traces offline and feed them into a model of the target hardware have gained popularity as they demonstrate good trade-offs between simulation speed and accuracy, particularly for early-stage design space exploration. We propose HetSim as a proposal to improve upon the state-of-the-art trace-driven simulation methodologies. HetSim captures crucial information in its traces that are lacking in prior work, such as tokens for PE-to-P communication, dependency annotation, and program counter tracking for prefetching support. HetSim introduces the notion of hardware primitives, where a primitive is any hardware functionality that can be emulated in software. Our latest HetSim release is packaged with a set of common primitives and is extendable to support user-defined primitives in the infrastructure. HetSim uses a high-level specification file that the user can easily customize depending on the target architecture. HetSim transcends beyond CMPs and can model any heterogeneous system and also scales tractably for systems with up to thousands of cores. The typical use case of HetSim when starting with a new architectural model is summarized here. The user implements the target architecture in Gem5 and connects modules called trace replay engines that are provided with HetSim. The user then modifies the specification to suit the target architecture, such as defining latencies for primitives based on the nature of the PE. Next, the user automatically generates a compiler plugin and tracing library. The user then implements their application using HetSim primitives and verifies the functionality of the application. The compiler plugin and tracing library are used to generate an instrumented binary, which the user runs to generate the traces for their applications. And finally, the user runs traces through the TRE-enabled Gem5 model to get all the required statistics. We used HetSim to model two target architectures. The paper focuses on evaluation with transmitter, which is a highly reconfigurable tiled architecture. We considered two hardware configurations that differ in the resource sharing mode. We evaluate three well-known workloads in linear algebra that show varying compute and data access patterns. Our experiments show an average speedup of 5x over the detailed model for this architecture, with timing deviation of 15% and power deviation of 11% on average. We also validated HetSim against a fabricated SPMM accelerating chip, and the evaluation against the chip shows timing deviations of 32% and 16% for the two phases of the algorithm. For more information, please check out my long talk and the repository. Thank you.